Okay, so I asked you guys to just take a quick look at this before class today. So this is going back to when we were talking about these things that I was calling closures, which is basically having one or more R objects sort of wrapped up with a function so that we can just use the data and have that data be associated with the function. So it's sort of a slick example that I showed you that we didn't go over that I said to take a look at and see if you could see what sort of the flow of things happening here is. So someone willing to take a stab at volunteering and walking us through what's going to happen when we execute this code? You guys aren't tired of hearing me talk by now? Somebody doesn't want to switch things up a little bit? So what happens when I call make container? What's going to happen? What's going to be the result of calling make container? Okay, so the result is a function. So why is it that the result of this is giving back a function here? So we execute make container, it assigns some things, and then it creates this anonymous function that doesn't have a name, right? And then what happens? Well, this is the last thing that's evaluated in the function, so that we know that the last thing, if you don't use return in a function, whatever the last thing that got evaluated is the thing that's going to get returned. So this function gets returned as the output of running make container. So what's the enclosing environment for this function? Right, the enclosing environment is the environment or the frame that was made when we went with, that is the make container function. And what's in that enclosing environment? Everybody's very quiet this morning. So what's in the enclosing environment? What objects are in the enclosing environment? X and I, right? Say it again?
N. Is N also there?
Is what also there?
N.
Oh, N, right. N would be in there too. That's sort of less germane for this, which is why I was sort of ignoring it. So, but the principal things we're concerned with are that X and I are in the enclosing environment of this function. So therefore, they are in the enclosing environment of boot means, which is this function here. And so when we then run boot means with, the result of this is just going to be some number from taking this mean of these data. Well, boot means when we run it with a number, boot means is this function. So if it gets run with a value that's not null, namely with whatever the number that comes out here, it's going to do this. It's going to have some mean value corresponding to this that gets passed in, and that's going to get assigned into x of I. But x and I don't exist within this function. So what does it have to do? It has to go look in the enclosing environment. It finds an I, and the first time this is called, it's going to find it and it's going to be 1. It finds an x, so it sets and because we're using this double less than assignment operator, it's able to assign into x the ith value of x, the first value of x, this value in the enclosing environment. So the x that gets modified is the x that's in this enclosing environment. So we can sort of think of this as here's boot means, here's the function, and then in its enclosing environment we have x and I. At the moment I is 1, and when we do that, when we do the assignment, the double less than assignment, it's assigning in to x of 1, it's assigning it in to be whatever that number is. Say, suppose this was 3.73 here. Then it's incrementing I, so it's setting this I to 2, and then it's returning, and it just keeps doing this because this is within a loop, so it's just going to keep repeating this process. So the slick thing about this is a way of basically sort of making this container of output values and not having to sort of keep track in this code of all of the indexing and that sort of thing, because the indexing is all hidden and wrapped up in here. And it sort of looks, and the side effect here is when we do this, we've been talking about R calling functions by value, but the result of this is we're having this pass by reference kind of effect, because these objects are bound up in with this function, and we're modifying them within this function, even though the usual operation in R is that we would have to return a value back in order to have a modifying effect. Okay, any questions about that?
It's crucial to have the if part of the anonymous function, right? Or otherwise you cannot get an X out of the function.
It's crucial to have what?
The first statement in the...
Oh, the return X?
Yeah.
It's nice to have it. We could actually get it. I think we could get it out of there by saying, if we had forgotten to put that in, we could probably do environment of boot means. That's going to give us this environment, and then in an environment we haven't really covered. We've seen this a little bit. We can do this, and then we could do that. So we could probably get it out like that, but that's sort of a pretty obscure way to get something out. So having it done this way is a much nicer way to do it.
Is this our way of having static variables?
Yeah, I mean, it's one way that you can then go about having these sort of global variables or sort of modifying things as a result of just calling a function. So yeah, I guess in some ways, yes. Okay, so let's go back to where we left off in terms of replacement functions. We are saying that when we do something like this, where we have an assignment, and on the left-hand side we actually have some R code as opposed to just the name of a variable, that there's a little bit more going on behind the scenes in terms of R is actually calling these things that are called replacement functions or replacement expressions. One of them is this diagonal of a matrix replacement that happens if you call code like this. And what I said was it's actually calling this function when you see something like that. So R is doing a little bit of magic behind the scenes to manipulate, it sees this expression when it's going through and interpreting the code, and behind the scenes it's actually basically doing this. And if we look at this function and actually look at the code of that function, what we'll see is that indeed at the end of that, it has a return of returning this X, which is the resulting matrix in which the diagonal has been substituted in for. And this then becomes the new value of the new value of this matrix, in this case of this matrix map. So what you would actually see if you looked at the memory address of mat, originally in the first line there, mat gets matrix, it would be sitting somewhere in memory. And then after we do the replacement, a new object would get created somewhere else in memory. The name of mat that was originally associated with this object is now going to be associated with this object. And this object in memory is sort of still sitting there in memory. It just doesn't have a name associated with it, so we can't actually go and get it anymore. And eventually, R is going to realize that thing doesn't have a name associated with it anymore. And it's going to tell the operating system, oh, you can use that memory. I'm going to release the memory back to the operating system for it to use again. So that's basically sort of the multi-step process that happens when these replacement functions get called. Questions or comments about that? So one of the reasons that I'm mentioning this is because if you have a replacement function like this that ends up modifying a very large object, you could have a big copy operation going on where you use a lot more memory than you realized if you didn't realize that this was going on behind the scenes. That's not always the case, and we're going to see when it happens and when it doesn't happen in a little bit. But that is something to be aware of. And we can actually write our own replacement functions as well. So we could write some code that will have this sort of slick effect. So here I'm just going to create a little list that has some information supposedly associated with me, and I'm going to create a new replacement function. And I'm going to do it with this syntax, with the assignment operator and then the name of the function that I want to use. And the effect of that is going to be to change the value of name within my list, and then any replacement function has to return back the object that is the new version of the object. And so I could start off with my name being Chris, and then I could say, oh, I want to use the replacement function. I'm going to set my name to be my full name. So obviously a silly example, but that's but this could come in handy sometime if you're writing code and you want to be able to do this sort of thing. Questions, comments? Okay. So I've made the point before that basically any object, anything in R is basically stored as an object, and that's true of functions as well, so we can pass around functions as objects. The other nice thing that we can do is oftentimes in R functions, we can either pass in a function as the actual function object, or we can pass in the function just as the name of the function as a string. So oftentimes we can either do something like, suppose there were some function f that takes another function as an input. So suppose it takes, so oftentimes I can either do something like this, where this mean is now referring to the mean function, or I can do this, and in many cases either of those will work. And the reason that often works is because there's a handy little function that you can use called match.fun that it will take in this and check to see, is that actually a function that's getting passed into me, or is that a character string that could be interpreted as a function, and it will behind the scenes handle figuring out which of those two things it is and making sure that the right thing happens. Namely that in this case that function actually gets selected, and in this case just gets evaluated on whatever this second input is. And if we wanted to evaluate a function where we knew the name of the function as a text string, we can also do something like this. We can say, here's a character vector just of length 1. I'm just going to create some x's, and now I'm going to evaluate this thing, but I'm going to say, treat this thing as the name of an object, evaluate it as a name, and then once I do this, I now am basically evaluating the function, and then I have to pass the arguments into that function. So this is an example, I think we've seen this a little bit before, of basically, one of the terms this goes by is called computing on the language. And you could imagine you could write some fairly involved code where you could actually sort of construct things as text strings and then evaluate them as R code. And that allows you to do some fairly powerful things. Then we'll see a little bit more of that at the end of this unit. Okay, questions? On a related note, if we think about what a function actually is in R, it basically, when we think about what a function is, it basically has three things. It basically has a list of arguments, the body of code that actually needs to get evaluated, and then an environment in which these things are going to be, in which the code is going to be evaluated. And so we can, out here I'm just creating three different functions, a simple one that just has a name of an object, and we'll return the value there, another that has a single R statement, and then another one that has a more complicated set of R statements in here. And if I actually looked to see what's the class of f, it'll say, oh, it's just a function. That makes sense. But I can also ask what's the class and what's the type of the body of the function, the code that's part of the body of the function. And for that original f that was where the body of the function was just an x, if I look at the type and the class of the body of that function, it'll just say, oh, it's a symbol and it's a name. So those are the sort of underlying kinds of objects, the way that R is treating that underlying code in the body of the function. In F2, it was a little more complicated. There was a whole statement there, and so if we look at the type and the body there, it says, oh, its fundamental type is it's one of these language things, and the class is it's an assignment, and that's because the expression in here is actually an assignment operation. And then a little bit more complicated in F3, which was this whole multi-line expression. It says it's also of type language, and its class is actually this squiggly bracket, which is a little bit confusing, but that's sort of the start of the code. And what we'll see in the later section of this unit is why it is that why it is that we get this as the result of running this code here. So that's really mostly foreshadowing for some of the stuff that we'll see in a little bit. And if you want to pull out the arguments and basically the set of argument names and what any default values are for those arguments, you can use this function called formals. And it's going to return this special kind of object called a pair list. And the pair list is just basically the matching of the names of the arguments with their default values. So in this case, x doesn't have a default argument, but y and z do. And so we see that the formals are there's x, there's no default for x, there's y, its default is 2, and then there's z, and its default argument is 1 over y. So if we were interested in sort of manipulating or looking at these arguments, we could do it in that way. Okay, so now the last thing I want to say, I think, about functions at this point in this sort of advanced treatment of functions is I want to talk about this idea called lazy evaluation. So let me switch over. I think I want to switch over to RStudio at this point. Let's go ahead and look at this example, which looks a little bit crazy, but once we understand how our R actually does things, it will make more sense. So what I want you to do is, whoa, I keep doing, okay. Could have sworn that was in here. Okay, here we are. Oh, that was the pair list was the output, not part of my code. That's why I couldn't find it. Okay, so what I want you to do is take a look at this code. Take about 30 seconds. Feel free to discuss it with your neighbor. And I'll tell you that this actually runs, and what I want you to tell me is why it seems strange that it runs. So see what seems funny about this code. And notice that the way I'm going to call the code is just by calling f with a single argument. Okay, so if I call f with 7, 7 is obviously going to get assigned into A. Right? And then it says B equals C. So what's starting to seem a little bit funny? Okay, so so there is no C, right? And there is no C, that's the default. And in fact, I haven't passed in B, so as Stephen said, neither one of them is defined. And then if I if I then start thinking about how this gets evaluated, C gets log A. Okay, that's fine. C is going to get log of 7, right? And then it says return A times B. So what do you think? I've already said this, it will actually work, but sort of if we weren't aware of that, what do you think would happen at that point?
You're going to be assigned with C.
Okay, so that is what will happen, but if we weren't sort of expecting that to happen, we would get to this and we would say, wait a minute, how can, B doesn't have a value in it yet because C wasn't defined at this point, right? So, yeah, go ahead.
I guess maybe it probably just like go to the line until it finds B. That's the moment where it gets.
Yeah, so that's actually what's happening. That's this idea of lazy evaluation that we know that default arguments will get evaluated in the frame of this particular function. So we know that B is going to look for C in this environment in this frame. So C gets assigned to be log A. Then we try and do A times B. And B at this moment, this doesn't actually get evaluated when the function first starts. What basically happens is R holds on to this thing called a promise that says, what's B? Well, B is just the expression C. And when we get to this point, it then has to actually do something with B and use B. It goes in, it tries to use B, and it realizes it's holding on to this promise that B is assigned to be equal to C. And at this point, C is actually defined to be log 7. So at this point, we get A, which is 7 times, and then it goes to look for B. It says it sees that B is set equal to C. It goes to look for C, and it uses that for B. But the idea is that the B equals C is only evaluated down here once R needs to do something with B. It's not done up here when the function is first called. Yeah.
Is there any way that you could use like a function, for example, you could use a concatenate operator, or
In the set of default, in the default argument?
yeah, because when I first saw that, I was thinking that might happen, but that's not something that's happening. Like it's defined as like an operator rather than.
Well, so you're saying you're asking if we could do something like A, B equals C of whatever?
Yeah, well, I was just thinking as the operators, then you would call on B with the argument to concatenate.
Sorry, I'm still not quite following. So is your concern that C is actually the name of a function in R?
Yeah.
Okay. So in this case, I guess I haven't said this explicitly before, but we can set C get to 3, and we can then say C of 5, 4, and we can also say print, or we could say D gets C. And it's okay that we have an object C and we also have a function named C, because R is smart enough to realize that if we do this and we say C and then open parentheses, it says, oh, I need to go look for a function named C. And if we do something like this, it says, oh, I need to go look for an object C and evaluate that. And so that should actually work. And part of what's going on there is that the function C is going to be in the environment of, say, of the base package, whereas this object is C is being created, this variable C that's actually a numeric value is getting created in the global environment. So if I said C gets 3, and then I say C of 5, 4, that's fine, and I say D gets C, D is 3. But if I said, let's say I said fun gets function, I'm just going to create a function that does nothing. So I can do fun, does nothing. But now if I say fun gets 7, and now I say fun, it's going to not work, because it's not, there are two different C's here. They're in two different places, whereas with my example of fun here successively being a function, stuff that's disappeared, and just the value 7, this is where this is getting overwritten here.
If you remove C and then define D as C, then what happens?
Then it should get the actual function C. So if I do this, let me remove C. Yeah, D is now a function. We should be able to see that's the same as the concatenate function.
Okay.
Yeah.
You can't, so then you can't use that in the argument line of a function call.
I can't use C, you mean?
Yeah, because then it will look for.
Well, okay, so right. So if we go back to this, the question is where it's, I guess this is an interesting question of where it's looking and why is it finding, so why is it finding this C as opposed to the concatenate function? That has to do with this issue of enclosing environments, which is it tries to evaluate these default arguments in the frame of the function. So the first C that it finds is this one. If it didn't find this one, eventually it would start marching up the enclosing environments, and presumably eventually it would find the concatenate function. But that's the first one it finds. Thanks, that was a good question. I think illustrated a lot of different
So
things.
returning R is actually a function.
Say it again?
The return in R is actually a function.
Yeah.
So environment or return function is actually C equals log A. That's why it works.
Say it again?
So return here is actually a function, and the enclosing environment for the return function is actually C equals log A, and that's why the lookup rule says when I cannot find B, I will find the C defined.
Not quite. So think about, any of you think about the problem on the problem set. If we think of return as being a function, where is A times B being, where is it getting A and B?
Enclosing environment.
Not in the enclosing environment, in the environment from which the function was called,
Yeah.
which is just, which is just f itself.
So if I have a C outside the function defined, the f function definition, then the C inside the f will never be used.
This C would, if the C were here and there were C out here, this C would still get used at this point because it tries to evaluate B. It looks in the calling function of whatever calls return, so it looks in here, and there is a C in there. So it would actually get this C as opposed to some other C. Other questions? Okay, so this idea of lazy evaluation also, we can see another nice example of this here, which might sort of puzzle us if we didn't understand lazy evaluation. So let's think about this. I'm going to create a function that all it does, regardless of its inputs, is it just prints out high. So I'm going to say, okay, to test this out, let me say, how much time does it take to take the mean of a million numbers? All right, 0.19 seconds. How much time does it take to evaluate this function f that all it does is print out high? 0 seconds, or under whatever the minimal amount is that is recorded by system.time. So then the question is, what happens if we call f with the argument, the input argument being the mean of r norm of the million? So do you think this is going to take 0, or do you think it's going to take 0.19? Okay, so why do you think it's going to take 0?
It doesn't care about it, we just evaluate it first.
Okay, so if we think about lazy evaluation, we pass this in, that comes in as x, but remember, x is not, the code that comes in as x is not going to get evaluated until it needs to use x. So it comes in as x, it starts to execute this, it prints out high, it never finds x, it never needs to evaluate that promise, whether the x is being set equal to this code, and if we actually worked with x here, it would actually evaluate that code to then tell us what to then determine what x is. But in this case, x is never used here, so it never needs to run the code. So it never actually does it. So this actually takes no time at all because it never actually does the mean. Or it never actually does the r norm and then the mean. Okay, questions about that? All right, so I want to go on to the next piece, which is sort of related in a number of ways, and think about memory use. So let me go back to the PDF. Okay, so one point I want to make here is that unlike in a compiled language like C, we don't need to explicitly allocate memory, but we've already seen in terms of efficiency that in some cases it makes sense to make sure to create an object in advance and then fill in the elements of that object. So that's sort of like, that's basically allocating memory and sort of getting around the fact that that in R you don't necessarily need to allocate it in advance. When we've used remove a number of times to get rid of objects, and one of the things to realize is that when we do remove, sort of like I was saying with the replacement functions, remove doesn't actually free up that memory for use immediately. So suppose I have some big object that's sitting in memory, let's say it's called x, and I say rm of x. That memory is still, that chunk of memory is still being used by R for at least a little bit of time, and it's not available either to R or to the operating system for other tasks. Because all that RM does is basically it takes the name x and disassociates it from that chunk of memory. What happens is every so often, and I think that this happens fairly quickly, R calls something called the garbage collector. It calls this GC function behind the scenes. And what the garbage collector does is it's sort of keeping track of chunks of memory and whether they have names associated with them. And so the garbage collector would notice that there was this chunk of memory. It had formerly been called X, but it was no longer called anything. And it would say, oh, we don't need that memory anymore. Let's basically return that to the operating system. And then the operating system or R, later on could make use of that again. We can actually force that garbage collection to happen using the GC function, but in general, that takes a little bit of time to do, and it's often not, because the garbage collection happens behind the scenes fairly frequently, there's often not really a reason to use that. But we'll see that GC can be useful for actually sort of monitoring memory use. So what I'm going to do here is I think I'm going to, for some of the examples in here, what I'm going to do is I'm going to do this just in a command line version of R, because I want to be able to stop R and start R again to sort of clean things out of memory for reasons that will, I think, become obvious. So I'm just going to switch over to just a command line version of R. If I do GC, it'll say it will basically say this. The terminology here is a little bit confusing. But the main things to see here, to notice here, the thing we want to concentrate is this thing called B cells. It's actually the memory sort of being used by R for our working operations. And it'll say how much memory is used by R in megabytes, 2.2 megabytes. And this is the maximum that was used in our current session. So there's a little bit of stuff going on behind the scenes, because obviously it's using a little bit of memory even though we haven't done anything yet. But I can do something like x gets R norm of 1 times 10 to the 8th. Any decimal number is going to take 8 bytes. We're going to talk about this in great detail in a couple weeks. So if I get 1 times 10 to the 8th numeric values, that's going to take up 1 times 10 to the 8th times 8 bytes, and we can compute how many megabytes that this object is going to be. So 1 times e to the 8 times 8 divided by 1,000,000 would give us megabytes. So this should take about 800 megabytes of memory for this object x. And if I do object.size, I can see that that should indeed be the case. So right about 800 megabytes if you sort of count off the zeros there. And we can also do GC and see what's changed. And we'll see that this now reflects the change that now, these are off by a little bit. I'm not sure what the difference is there. It may have to do with exactly, sometimes these things are in terms of sort of base 2 and base 10 versus base 10. And I don't want to get into those details, but we're often not worried about, for being precise here, but more or less this is taking 800 megabytes, and essentially the maximum used in our session is 800 megabytes. So the GC is reflecting the fact that we've created this large object here. And if I remove x at this point, and then I do GC again, you'll see that now it's dropped back down to 2. That's sort of the active amount of memory being used, but the max used is still 7 or 8. It's still around 800 because that's how much we've used at most during our session here. Okay, questions about that so far, or about sort of what I'm doing here in terms of thinking about memory use? I'm going to avoid that question. I don't actually. So I think some of the names here are relics of sort of when R was first being created and sort of some of the stuff that's going on there under the underlying level in terms of C in the operating system. And so I don't actually know. This has something to do with sort of some system level stuff that's going on, but I can't tell you in any more detail what's going on with that. Other questions? Other questions I can't answer? So let's now think about when memory might be used in a hidden fashion. So if I just also include in here a handy little function that will print out the 10, well, by default it prints out the 10 largest objects in our current working environment. So this is something I have in my R profile file, and I find to be useful. And so if you're interested, you might use that yourself. This is actually the result of a problem on the problem set from last year. So this is the result of my solution and some ideas I got from the student answers from last year. The other thing I want to point out is another useful function that we'll use a little bit, which is this function called inspect. And it turns out this function is sort of an internal function that R doesn't mean to be used by novices. So you have to call .internal, which basically allows you to use this sort of hidden function. And so I just want to, so you guys are now getting to know R, getting to be the level of expert R users. So you're now qualified to use functions like this. And what we're going to see here is I've created this object A, and then I'm going to inspect it. And what this shows me is a few different things. It actually shows me what's stored in the object. This is the thing that we're going to be looking at a lot. This is actually the memory address of where that object is stored. And it's in some hexadecimal base 16 number. This is something you might run across every so often. This is the underlying C representation of a numeric decimal number in R. So it's a real, and it's this thing called an S expression. The S stands for S, which is the precursor language to R. This stands for expression. So at the underlying C level, a vector of 5 decimal numbers is stored as one of these real SXPs and is stored in that location. So then knowing that location or being able to query that location is going to be handy for us to see when memory is being used behind the scenes that we might not otherwise realize. So that's the point of having seen that. Okay, so I'm going to do this again back in my command line R because I want to be able to clean things out. Okay, so I'm going to create a vector of 10 million numbers. You'll notice that this has used about 80 megabytes. That makes sense based on our calculations before. Before we had something that was 10 times the size and it was about 800 megabytes. Here this is about 80. I'm going to actually make this into a matrix by setting its dimension to be 10,000 by 1,000. And then I'm going to set the diagonal of that matrix. It's not a square matrix, so it's only going to be, I guess, 1,000 values, or we have to figure out the dimensionality. But this is setting the diagonal values to be 1. And now the question is, how much memory was used in the process of doing this? So that's the thing. That's the question that I want us to focus on. So if we now do GC, what we'll see is the current amount of memory being used is the same as it ever was. But the interesting thing is we notice the max used is now essentially double what was initially used. So what this is saying is that somehow or another there's some hidden use of memory going on that is not immediately obvious to us unless we think about what's happening in these two lines of code and think about what's going on behind the scenes. So that relates to this idea of replacement functions, which we just talked about a little while ago. We already saw with a replacement function that a new object was getting created when we replaced the diagonal, and the name was being transferred from the old object to the new object. So I've actually lost my opportunity to do this, so let me quit out of this and do this again. So I'm going to do my .internal.inspect trick. So it says it's at memory location 104.8.0.0.0.0.0. And now I'm going to do my dim. And now let's do that again. So you can see that just changing the dimension hasn't changed the memory location of my object. This is still the same as it was here. So in memory, this object X is still just stored as one very long vector. It now has some attributes associated with it that tell R how to format it in terms of printing it out as a matrix or subsetting it in terms of a matrix. But its underlying structure is still just this very long vector. But as soon as I do the diag of X gets 1, if I now do this, we can see it has a new address in memory. So that's this idea that I've already sort of talked about with my hands, that originally there was this object, the new object got created in which the diagonal had been replaced, and the name got transferred from here over to here. And so this is the new memory address, and that was the old memory address. And eventually, we've already seen that when we did GC, we saw that this memory had gotten cleaned up and sent back to the operating system because we saw that the current memory being used was only the 80 megabytes for this object. So those other 80 megabytes are no longer being used, but they briefly were both being used at the same time, which we saw indicated by the fact that the max used was about 160 megabytes as opposed to the 80. Okay, questions or comments about that?
So for the normal assignment operator, it won't create a copy of your object.
You mean if we just assign something afresh? I mean, if we just do X gets R norm of whatever, this hasn't existed yet, so it has to create the
So if
memory.
I want to change like
An element of X. Okay, so that actually leads nicely into I think what we're going to look at next. So let's go back to, I guess, to the PDF. Okay, so this was the example we just saw. This is under 3.3. Now let's look at it this way. Again, I'm going to go back to my sort of simple version of R, but just to show you what we're going to do. We're going to create that random normal again, look at its memory location, and then assign into a single element of X, and then see if it's actually done a wholesale copy of the entire vector. We might hope that it hasn't, because all we've done is change one little piece, and if that causes us to then recreate that entire vector, that seems quite wasteful. So let's see, I guess I'll go here and make the, copy the code. All right, I'm going to clean things out again. Oh, it's interesting. This is the same address. It looks like it's reusing the same address as from our last version of R. So I make X, I look at its memory address. I assign into the fifth value. So this, again, is one of these replacement expressions. But we see that in this case, that what's going on in the guts of R in terms of how it handles things, that the new X is actually not new in any sense. It's just the same object. It's still called X, and it's still at the same memory location. So there was not a copy made of the entire object. All it did was it knew to go into the fifth place and just substitute in. And so basically what's going on is there's a called the C code, compiled C code being made here, where R basically just goes in. This vector X in C is basically, it's an array, it's a pointer, and in C we can go into the fifth element and just substitute in just with some very simple C code. And that is what's actually happening in R, because it just calls that C code. And interestingly, if we do GC at this point, we see the current usage is 80, and the most ever used was about 80 as well. So it's not making, this is confirming that it's not having made a whole new copy of X, because if it had, we would presumably see that was around 160. Okay, I think I won't dwell on this, but I'll just say I sort of mentioned this before when I briefly mentioned that PQR, that new engine for evaluating R code. That if you do something like this would use up 80 megabytes because that's how big that object is. If I do this and do some subsetting, this is actually going to create another vector 1, 2, 3, 4, 5, all the way up to the length of X minus 1 in this case. So that vector itself is going to take up a chunk of memory because it's a fairly long vector. So we're basically going to be taking up the memory of X and the memory of this temporary vector, and then indeed also the memory that's going to need to get allocated for Y. So there are actually going to be 3 big chunks of memory being used here and not 2, which is what you might have expected if you didn't think through what's happening, if you didn't know what R was doing sort of naively with the colon operator there. Yeah, Dustin?
So this means that if you're more conscious about memory usage as opposed to computer efficiency, then you would rather do some of the for loop instead of factor calculation?
Oh, that's interesting. Yeah, so there might, in some cases, like you say, be sort of competing objectives that if you didn't want this object to ever be created, I suppose one way you could do this is you could actually write a for loop and substitute in one at a time. So that probably wouldn't arise all that often, but there might be occasional times that you were so concerned about memory use that you did something to get around it that made things slower, but didn't actually use up more physical memory. The other thing that I should mention at this point is, I think I've said this statement many, many times, so I've sort of forgotten whether I've said it in the context of this class, which is that if you actually run out of the physical memory on the machine, your program will not fail. It will start, the computer will start using hard drive space as a replacement for the physical RAM, the physical memory on the machine. So in some sense you're okay, but in a real sense you're not okay, because as soon as it starts using hard disk, it's much slower to be able to operate off the hard disk as memory than it is to actually operate off the RAM of the machine. So in most cases, if you start what's called swapping or paging, which is that you run out of physical memory and you start using the hard disk, your code will basically slow to a crawl, and in many cases it will essentially never complete in sort of finite time, or it will take a very, very much longer than you would expect it to take. So in general, you want to try and make sure that running your code doesn't cause you to be in this condition of actually running out of physical memory on the machine. And oftentimes, for reasons that I don't fully understand because I don't really understand hardware all that well, if you get up to using like 80, 70, 80, 90% of the physical memory on the machine, you're going to start to see things really, really slow down. And you're going to probably this is because there's the overhead of doing whatever else the machine is doing, as well as the core calculation that you're doing. So what you'll see is, if you're running R and your machine has 8 gigabytes of RAM and you have an object that takes up 6 or 7 gigabytes of RAM, and you start working with that, or you start creating that, that code will slow down. The operating system and your graphical interface to the operating system will also slow down, because there's going to be all this competition for memory because the operating system is running low because it's trying to do these various things. So you generally want to try and avoid that. I think I'm going to skip over this for the sake of time, but basically when you call C code from R, more memory can get used than you might expect, because C is actually going to use, in many cases, the same memory as R is using for an object. So you can basically often pass an object to C code. C will use that same allocated memory that R had originally allocated. So there's not a copy made in that sense. But when C passes the stuff back to R, there's generally going to be a copy made at that stage. So oftentimes when you call C code, if you know how to, or you learn how to use .c or .call or RCPP, some of these ways of calling C code from R, there will be copies made in the process of doing that. And the other thing that often happens when you call C code from R is you need to make sure that the types match. So you need to make sure that if your C code expects an integer versus a double, namely a floating point or a decimal number, you need to make sure that the R object is actually either an integer or a real to correspond to that. And so sometimes you'll need to do this coercion like as.integer or as.numeric. And that, if you start out with something that's a double of a decimal value here and you do as.integer, then a copy is going to get made at that point. So that's where some of these copies and additional memory use can happen when you're calling compiled code. So if you're interested in that, I'm not going to dwell on that here, but there's an example in here that you could take a look at, and we've sort of seen the tools that I use to understand and investigate what goes on here. So you could look at that yourself. So the other thing I want to mention is this idea of something called copy unchanged, which is that when you make a copy of an object in R, it doesn't always immediately make a copy of that, explicitly make a new copy of that object such that there are now 2 objects existing in memory. So we'll see a couple examples of that. And R is somewhat, although not quite as smart as it might be in doing this. So if I do this, I'm going to create this little function f. It's again one of my sort of silly little functions again, because it's just meant to illustrate things. But what you'll see is that all that f does is it assigns to z the first element of its input x. It just prints back. I'm not sure whether this will actually print out. I might need to wrap that in a print statement. It looks at it's going to give us back the internal inspect information, and it's going to return x. And so I'm going to take y, create an object out of it, and I'm going to assign to out the evaluation of this function on y. And we're going to see what happens in terms of how many new objects get created. So if I put the GCs in here. They're not going to be very helpful, maybe, because I haven't sort of cleaned things out, but might not be too bad. So okay, I've made y. I can look at the memory address of y. It's this 1054C5000 address. And now when I do out, and it did actually print out. So you'll notice that this printout here is coming from this call to internal.inspect within the function f. And so apparently the x in here has the same memory address as my original y that I passed in. So it didn't actually make a copy of y when I passed it in and there was an x in there. They're both pointing to the same memory address. So there's y sitting here in the global environment, and then in the function f there's this argument x, and it's actually just a name that's pointing to the same place as y is. So there hasn't actually been a copy made. And indeed, if we do internal inspect of out, we'll see that's also pointing to the same place. So out is itself also this 1054C5000 location. So there's this one block of memory, y is associated with that block, out is also associated with that block. So why don't we quit there, and when we come back on Friday, we'll delve more into this and get a better understanding of what's happening and when copies are actually made in this context.